So today we're going to learn about speed and velocity. So again, new terms. I'm sure they look familiar because we use them in English all the time. But just like yesterday, there's going to be a difference between them and how we use them in physics. So first, speed, we give the symbol v, and velocity the symbol v with an arrow above it. Remember with what we went over yesterday, this should tell you that speed is actually a scalar quantity, which means it only has a magnitude, for example, 100 kilometers per hour. And velocity is a vector quantity. So for example, 100 kilometers per hour north. So that's the main difference between speed and velocity. Okay, now, however, most things don't move at a constant speed. For today, we will be keeping things at a constant speed, but most things either speed up, slow down, and in the case of velocity, even if your speed is the same, if you change your direction, that's still considered a change. Okay? And therefore, all those changes are, we call them accelerations, and that'll be for tomorrow's lesson. But for today, we're going to talk about average speed and average velocity. Okay, so average speed. To find the average speed, here's the equation, and we do have the equation on your handout as well, right here. So average speed is your total distance, notice there's no vector sign here, over a time interval. Okay, both of them are given delta signs because they have a start point and a finish point. It's like your distance, if you're measuring something, go from here to here, start, finish, that's a change. Right? Time as well, if you're timing something from here to here, right? You're not recording one point in time since the beginning of the universe, you're just timing an interval from A to B. So we both put the delta signs on both of them. And the small capital T, written as a subscript, just means total. Okay, for velocity, it's the exact same equation as speed, except we put vector signs over them. Okay, and remember that there is a difference between distance and displacement in how we actually calculate them with what we did yesterday. Now the great thing is with this equation, we only have 3 variables, so it's very easy to rearrange, and we can use this triangle to help us if you've used triangles before to help you with rearranging. Okay, so you can think of, say, velocity equals displacement over time, or you can think of displacement equals velocity times time, or time equals displacement divided by velocity. And so we're going to use these equations to solve lots of problems today. And so getting back to the PowerPoint, we do have units for speed and velocity. They have the same units. The only difference is, remember that velocity includes a direction. Now, usually we're familiar with kilometers per hour. That's the one we use more frequently on a day-to-day basis in our real lives. However, the SI unit, the Standard International Unit for Speed, which is the one we're going to be using in all of our equations, is going to be meters per second. You remember during the math skills lesson, we learned how to convert one to the other. So if you want just a recap on that, if you have, say, 100 kilometers per hour, say a speed limit on a highway, and you want to know how many meters per second that is, divide by 3.6. And that'll give you how many meters per second 100 kilometers per hour is, which is 27.8 meters per second. But obviously when you go on the highway, you don't see a sign that says maximum 27.8. That's just, we don't use that on a day-to-day basis. Okay, and of course vice versa. If you wanted to go from meters per second to kilometers per hour, instead of dividing by 3.6, you would multiply by 3.6. Okay, so let's use this to try and solve the first couple questions. First question below. Here we have a dog runs in a straight line for a distance of 43 meters in 28 seconds. What's the dog's average speed? All right, so we're going to solve this with a method. I'm going to write lots of details. When you're answering these questions, you don't have to write as much details, but we're going to use the grasp method if you're familiar with it. So G stands for given. So we need to look at the question and say, okay, what are we given? What do we know? Well, we know distance. So our distance is 43 meters. We also know time. Time is 28 seconds. Okay, what are we required to solve for? Okay, what are they asking? Speed. Right, so we want to know average speed. Okay, then we're going to analyze, meaning what equation is going to help us. So you can look at your equations, you have a formula sheet, you can see, okay, based on what I know and what I need, what equation is going to help us. In this case, it's the equation that I give you from today's lesson. And so average speed equals distance over time. Okay, now we're going to solve. So average speed, we can plug in distance and time with our given, so 43 meters over 28 seconds. We use our calculators, we get 1.5 meters per second. Now, physics really is a course in translations, right? We're using two different languages. We're using English and mathematics. So a problem always starts with English, but then to solve it, we translate it into math, and we solve the math. But to finish, of course, you need to finish by going back into English. So you need to paraphrase. I'm going to say paraphrase, you can write the dog's average speed is 1.5 meters per second. Okay, just going to pause there to see if anyone has any questions. All right, so our second question. I'm going to do the same thing, except again, I said you don't have to write grasp. You don't need to write G-R-A-S-P, but you should still show that work so I can see what you're doing. So let's try this question. A baseball rolls along a flat parking lot in a straight line at a constant speed of 3.8 meters per second. So what I like to do as I'm reading the question, I'm like, oh, constant speed. So I just write speed equals 3.8 meters per second. And that's part of my given. Then you continue reading. How far? It wants to know distance. All right, so distance is what I'm looking for. Will the ball roll in 15 seconds? Okay, so sometimes it doesn't actually say what the variable is. Like this one, it says constant speed of, so fairly easy to pick out. Oh, speed. This one's fairly easy to pick out too because it's in seconds. And later when we get to different variables, they're a little harder to pick out. Just remember this. Sometimes it's really easy to determine what the given information is based on its unit. Since this is a unit of time, it's obvious this is for time. So we're going to write delta t as 15 seconds. All right, so now we need to analyze. We can go back to our triangle here. We're given velocity. The delta represents, we always write a delta when we want to talk about change. So when I mean change, when you look at distance, I explained the difference between distance and position. So position is where you are relative to something, and distance is where you've moved from where you were before. If you moved somewhere compared to where you were, that's a change. And so if it's if the variable represents a change, we put delta. That's what the delta stands for, change. All right, so in this case, since we're looking for distance, right, we can use the formula distance equals velocity times time. So we're going to write distance equals velocity times time, which is, based on our given, 3.8 meters per second, times time, which is 15 seconds. Get our calculators out and we'll get 57 meters. Okay, and then we can paraphrase and write, therefore, the baseball rolled 57 meters. Okay, I'll just pause there. So our first couple examples had to do with average speed, and that's a scalar quantity, no direction. Average velocity, that's a vector quantity. So we're going to have to do displacement over time instead of distance over time. And remember that displacement is your change in position. It compares where you were before with where you are now. And the path that you take to get from where you were before to where you are now doesn't matter. Okay, so let's go over some examples to see what I mean by that. We'll go back to our handout and we'll do number 3 together. Number 3 says, on a windy day, a balloon's position changes as it is blown 82 meters north. So notice that we now have a directional property. So this is a vector. And a change in position is our displacement. So let's write displacement, put the arrow, symbolize it as a vector, equals 82 meters, and in our square brackets we will write our direction, north. Away from a child in 15 seconds. So that's our time. What is the average velocity of the balloon? So we're looking for average velocity. Now to do that, again, it's the same equation. It's just instead of writing distance over time, it's displacement over time. So average velocity is displacement over time, which we are given 82 meters north over 15 seconds. Put that into our calculator and we'll get 5.5 meters per second. And the direction will be the same as our displacement, north. Then we just need a paraphrase. Therefore, the balloon's average velocity is 5.5 meters per second north. And we just pause. Alright, so question 4 says a subway train travels at an average velocity of 22.3 kilometers per hour west. Alright, so they're telling us average velocity, which is a vector. And you can tell because they have their directional property. But they're not giving the information in SI units. At least base SI units anyways. So we need to change the kilometers per hour into meters per second. We have kilometers per hour west. And to do that, we are going to divide by 3.6. So when we do that, we get 6.19 meters per second. And the direction is, of course, the same. Then it says, how long will it take for the train to undergo a displacement of 241 meters west? So our displacement is 241 meters west. So if we looked at our equations, in this case we're given displacement and velocity, so time would equal displacement divided by velocity. So let's write down our equation. Time equals displacement over velocity. Then we're just going to input our values. It's very important you input the one with meters per second if you don't input the one with meters per seconds, well, kilometers doesn't cancel out with meters. And so when we're dividing, we want them to cancel out. So our displacement is 241 meters west, and velocity is 6.19 meters per second. So when they're both in meters, meters will cancel, and we're going to be left with seconds, which is our time. It's 38.9 seconds. Okay. Then we can paraphrase, therefore, it will take the train 38.9 seconds. All right, so question 5, the last question for today, it has a little bit of a twist in it. Because up until now, we've looked at average speed and average velocity as being pretty much the exact same thing, except one just has a direction. In this case, we're going to see very, very different answers. So here we have a jogger. It takes 3.5 minutes to run once around a square city block that is 220 minutes on each side. So let's draw a sketch of the motion. It doesn't say draw a vector scale diagram, so we don't need a scale or anything. We're just going to draw what's happening. So we're going around a city block, so maybe we'll start here. And we'll go this way, which is 220 meters. We'll go this way, which is 220 meters, because it says on each side. And then this way, which is 220 meters. And then back, which is 220 meters. Okay? And the amount of time it takes to do that, it says, is 3.5 minutes. But again, minutes isn't the base unit of time. So we need to change that into seconds. So 60 seconds in a minute, we'll multiply by 60 seconds per minute. We'll have 210 seconds. So we know the amount of time it takes now. Part B says determine the jogger's average speed. Speed, scalar, we don't care about direction. Let's put A. So speed, since we don't care about direction, is simply distance over time. And distance is 220 plus 220 plus 220 plus 220, or more simply put, 4 times 220 meters. 1 for each side. And a total time of 210. Sorry, you can't even see that. Let me move that up. There we go. So speed is distance over time, which is 4 times 220, 1 for each side, and a total time of 210 seconds. So when we look at what that is, we get 4.19 meters per second. So we can write our statement, therefore, the jogger's average speed is 4.19 meters per second. And of course, there's no direction because speed is a scalar quantity. For part C, it says, what is the jogger's average velocity? So that's a vector. Upon returning to the starting point, it means going from here and all the way around and coming back here. So in that case, your displacement is not 220 meters. That's how far you traveled. Remember, your displacement is change in position. How has your position changed if you started here and you finished there? For somebody who looked at you and then closed their eyes for 210 seconds and then opened their eyes, it's you in the exact same spot, they would say, nah, you didn't move. And for a vector quantity, that's the truth. Your displacement is 0. So now, when we're to calculate average velocity, which is displacement over time, we get 0 over 210 seconds, which is 0 meters per second. Now that is a directional property, but since we're not moving anywhere, we don't need to write in what direction we're not moving in. It doesn't make sense. But this is a good example. I like this example because it shows that it's not like you're just going to get the same number for speed and velocity. It's just one has a direction, one doesn't. The way we calculate displacement is completely different. Even if you were to go from here to here to here and stop here, your distance would be 220 plus 220, which is 440. Right? Your displacement would be whatever the length of that hypotenuse is. And that won't be 440. It'll be something less than that. Okay, so there's a very big difference between average speed and average velocity. Okay, so I'll pause there, see if anyone has any questions.